I hope you're all well. Right, what an honor tonight to have once again Professor Ian Newton to come and give us a lecture. He's given us talks on sparrowhawk and also a much larger talk about bird migration a while back. He is undoubtedly, for people like myself and all my colleagues, the most senior ornithologist in the country. So having him come to Hoss is very special indeed. Ian was born and raised in Derbyshire, but he graduated from the universities of Bristol and then Oxford, receiving doctorates in philosophy and also science. As a teenager, he became particularly fascinated by finches, best known for his amazing work on raptors and a 27-year study of the sparrowhawk. Professionally, though, he became senior ornithologist at the Natural Environment Research Council, and he was also head of avian biology at the Monkswood Research Station. He's put a lot of time in for organizations that protect and help study birds. For example, he's been chairman of the Peregrine Fund, chairman of the RSPB, chairman of the BTO, president of the British Ornithologists Union, president of the British Ecological Society, and no doubt other things too that I don't know about. He's also visiting professor of ornithology at the University of Oxford. Now, Ian's written 11 major books. The most relevant one tonight is, well, there are 3 to do with bird migration. This is one of the favorite ones for me from the New Naturalist series, now available as a paperback. And he's done hundreds, co-authored hundreds of scientific papers. The book on migration and ecology of birds he first did, it was in 2007. The New Naturalist book was in 2010. And tonight, he's going to be giving a distillation of much of what is in that New Naturalist book, which is an absolute masterpiece about bird migration. So Ian Newton, thank you so much for coming along and joining us tonight. And we look forward greatly to hearing your talk about bird migration. Over to you, Ian.
Ian, would you mind just unmuting yourself, Ian, if you can, and then we'll get underway. Keith, thanks for that intro.
No problem.
Perfect.
Can you hear me?
We can, Ian, loud and clear.
Yes, well, thank you very much indeed, Keith, for those very generous remarks. And good evening, everyone. It's a pleasure to get the chance to talk to you again about bird migration. Now, migration in birds, as you all know, is often defined as a regular return movement that birds make between their breeding and their wintering areas. And migration occurs not just here in our climate, with warm summers and cold winters. It also occurs in the tropics with regular wet and dry seasons. In fact, migration occurs in any seasonal environment in which bird food supplies change predictably from abundant to scarce during the course of each year. Mostly, of course, birds move from high to low latitudes for the winter. Can we have the next slide, Barry, please? This is slide 2. I've got one up on shearwater migration. Is that, I hope you've got a different one. No, you've got to go back to the beginning. That's it. So we're all familiar with the fact that within Britain, we have resident species of birds that are present with us year round. Birds like wren and blue-tit and house sparrow are in this category. We have summer visitors that come here to breed, birds like swallow, cuckoo and osprey. And we have winter visitors like redwing, fieldfare, brent goose and so on. We also have passage migrants that occur each year in spring and autumn as they travel between breeding areas to the north of Britain and wintering areas to the south of us. Birds like little stint and grey phalarope are in that category. But there are also, and this is probably the biggest category, what we call partial migrants. These birds include birds like blackbird and linnet and kestrel. These are birds where part of the population stays here year round and another part migrates away. And the two sectors of the population interbreed in the same area. And within those populations, some individuals might migrate in one year, but not the next. Well, why do birds migrate? Next slide, please, Barry. The answer is obvious from this picture taken in my home village in winter. Migration is assumed to occur wherever birds benefit from leaving their breeding areas for a period than by staying there year round. And the usual reason that breeding areas become unsuitable during part of the year is, of course, lack of food. As plant growth stops for part of the year, and many of the prey organisms of birds die off, or hibernate, or become inaccessible under snow and ice. Next slide. In the case of these whooper swans, lakes in the breeding areas freeze over in winter. And in the case of swallows, next slide, the aerial insects on which they depend become unavailable in winter. And at high latitudes higher than us, day lengths also shorten in winter to such an extent that many diurnal birds would have insufficient time to get enough food, even if food were available. So the reason why many birds move south to lower latitudes in autumn is, I think, fairly obvious. But a much more difficult question is whether they bother to come back in spring, when their wintering areas, many in the Mediterranean region or in Africa, seem perfectly capable of supporting them year round. Next slide. But by returning north in spring, birds can exploit the seasonal abundance of food at high latitudes, as well as the longer summer days, and probably raise more young than if they stayed at lower latitude wintering areas and competed with the birds that are resident there. So whereas the advantage of migration to lower latitudes can be seen as improved winter survival, the advantage of spring migration to higher latitudes can be seen as improved breeding success. And migration occurs when the net benefit of moving both ways outweigh the costs of staying in breeding areas year round. But these are just plausible ideas, and it's practically impossible to test them experimentally. But nevertheless, there's considerable circumstantial evidence for them. Next slide, please. If we take, first of all, the geographical trends in birds migration. If we take the western seaboard of Europe, from Morocco in the south up through Spain and France to Svalbard in the north, you can calculate for each line of latitude, or 5-degree line of latitude, the proportion of breeding species that move out to winter further south. And these proportions are shown in the pie charts on the left there. And as expected, the proportion of migrants among local breeding species increases with increasing latitudes northwards as winters get more severe. But even in the mild climes of Morocco at the bottom there, 30% of all breeding bird species are completely migratory. And this proportion increases with latitude, reaching more than 90% in the far north. Next, please. Species that winter in the far north, with at most only a few hours of twilight in midwinter, includes birds like the ptarmigan and the snowy owl shown here, and some seabirds that feed at cracks in the pack ice. But the important point is that a geographical trend occurs which corresponds to the severity of winter, to the difference between summer and winter food supplies. And this trend, of course, occurs and operates worldwide or around the Northern Hemisphere. Now, whether particular species leave particular latitudes relates to their diets and whether the foods they eat remain available at that latitude in winter. Next, please. Well, that's migration as it is, but a current interest, of course, is in seeing whether bird migration patterns are changing in relation to climate change. And during the last several decades, several types of change have indeed occurred, as listed on the slide here. Many birds that were formerly totally migrant are now becoming resident. They're staying in their breeding areas year round. Others, as we know from ringing, are shortening their migration distances. They're wintering further north, not migrating as far south as they used to do. Many birds are changing the timing of their migrations. They're arriving here earlier in the spring and they're leaving earlier in the autumn. So birds are clearly changing their migratory behavior. Next, please, Baron. Just to give you an example here, the lesser black-backed gull used to be totally migratory in Britain. In the 19th century, virtually no birds stayed in the winter, but now, as you know, a large proportion of the population stay here through the winter, although many of them, particularly the young birds, still continue to winter off West Africa. Next, please. Another example of a change is the chiffchaff, which was first recorded in winter in British gardens in the 1940s, but in the decades since then, the number of records each winter has begun to increase, and the bird is now more widespread in winter, although still not common. So clearly some birds at least then are changing their migratory behavior in ways that would be expected if the changes were due to global warming. Next, please. Oh, this is just a trend. I wanted to show the trends in arrival dates over the years. This is a graph, as you can see, with the years along the bottom. It runs from around 1960 up to the mid-1990s, and the dates are given on the vertical scale there. And it shows the dots. Each dot refers to the year, and it shows the first arrival dates of these migrants in bird observatories in southern Britain each year. And the arrival dates, as we all know, vary from year to year. In very warm springs, the birds turn up earlier than they do in cold spring. So the arrival dates fluctuate from year to year. But the general trend in both these species over that 35-year period is that the arrival dates have become progressively earlier. The difference between those two species has still been maintained throughout, but the general trend is there. Next slide, please. Well, I now want to look at some of the adaptations to migration. Will all of us know, I think, that migratory birds put on body fat in order to fuel their journeys. But the amount of fat that birds put on varies with the types of journey they have to make. And birds like this linnet, because it travels relatively short distances over land, where food is readily available almost anywhere it might stop, linnets put on only a relatively small amount of fat. They increase in body weight by about 10% at migration time. Next, please. But birds like this sedge warbler that have to cross the Mediterranean Sea and the Sahara Desert, they put on much more fat. Next, please. This is a photograph of a lean sedge warbler. Contrary to what you might think, this bird is perfectly well and alive, and all that's happened is that its breast feathers have been wet and brushed aside so that you can see the breastbone, the chest of the bird, underneath. And at the top of the breastbone, at the top there, you can see a patch of yellow, which is fat under the bird's skin there. That's in the wishbone, as you might like to say, or in the tracheal pit, as ornithologists call that area. And if you catch a sedge warbler in winter or summer, and you brush aside the feathers, that's what it will look like. And that fat accumulates during the course of each day as the bird feeds to provide a reserve to carry the bird through the night and over onto the next day. But if you look at a sedge warbler, next please, Barry, that is about to start migration, it looks very different. This bird is also alive, and you can see on the same treatment, the feathers have been wet and brushed aside, but you can see that yellow color. That bird about to migrate, its body is totally encased and ensheathed in a fairly thick layer of fat to fuel the journey. And sedge warblers are among birds that absolutely double their weight just before migration. And it's been calculated that that is enough fuel to allow a sedge warbler to fly non-stop from southern Britain to south of the Sahara, where it will spend the winter. We don't know that it actually does fly that distance non-stop, but it would certainly not need to feed on the several day journey involved. Now that bird, I remind you, is in terms of weight, it's actually smaller than your little finger. Now, these photographs are from wild birds, misnetted, but in captivity, birds also put on weight at migration times, and that gives us another indication that those birds are in a migratory state. They're ready to go, even though they're in captivity. Now, next slide, please, Barry, shows the fattening rates of sedge warblers as studied in Africa in spring for their return journey to Europe. And you can see the dates are given along the bottom, and the body weights of the birds are given at the side there. And each of those lines refers to an individual sedge warbler that was caught on 2 occasions. And you can see it's during a period of fattening, and those birds are putting on a vast amount of weight. And the whole fattening takes about 10 to 14 days, we can say, during which time the body mass of these birds doubles. Next, please, Manny. Well, why do birds put on fat and use it as fuel? It is, in fact, the most efficient fuel that any bird could use, giving more energy per gram than high-octane vehicle fuel. And for any flying animal, it is, of course, important for it to minimize any weight gain if it's got to fly. And what I've done here is to list the 3 possible fuels that a living bird might use to migrate, either fat, carbohydrate, or protein. The carbohydrate in a bird will be in the form of glycogen concentrated in the bird's liver. And the protein is, of course, mostly muscle. The column of figures in the middle there simply shows in kilojoules the amount of energy that is released by metabolizing 1 gram of those 3 types of tissue. And you can see immediately that 1 gram of fat will yield 7 to 9 times as much energy as 1 gram of either carbohydrate or protein. Well, one reason for the efficiency of fat as a fuel is that fat can be stored in an animal's body, including our bodies, with very little water. If you take fat adipose tissue, it contains on average only about 5% of water, whereas carbohydrate and protein contain 70 or more than 70%. That's basically muscle. That is one reason why fat is such an efficient store of energy, because it can be stored with very little water. But the disadvantage of fat is that its breakdown, its metabolism, requires the breakdown of a small amount of protein too. So whenever birds are putting on migratory fat, they also lay down a certain amount of extra protein in the muscle at the same time to cope with this requirement. Well, I want to move on now, next slide please, Barry, to talk a little bit about the various ways in which we study bird migration and the lessons that these methods have taught us. Well, at the start of the 20th century, bird ringing represented what was, in effect, a huge technological advance. As you know, each metal ring bears a characteristic number. So for the rest of its life, a ringed bird remains as an identifiable individual, yielding in the collective recoveries from many individuals information on the lifespans and movements of each species. And most of what we know on bird migration routes is still based primarily on ring recoveries. Next, please, Mary. But ringing isn't a perfect method. One problem we have with ringing is that the recovery rates of some species are extremely low. From more than 1 million willow warblers that were ringed in Britain over the last 100 years, only 0.25%, that's 1 in 400, have ever been recovered. And most of these were recovered back in Britain, so they tell us nothing about where willow warblers migrate. But we do have some useful recoveries in this respect. Next slide, please, Barry. And these are all the recoveries of willow warblers outside Britain. And they indicate to us that these birds migrate down through France and Spain to winter, probably in West Africa. It's possible that some birds go further, but there are no ring recoveries to prove this. This is taken from the BTO Atlas. Well, a second problem of bird ringing is that it's virtually impossible to get ring recoveries from some parts of the world, even though we suspect our birds go there. We may be dealing with a population that's not sufficiently literate to report the rings, or there may be political problems, so we don't get them. Next slide, please. But another useful method of studying bird migration, which you'll all be well familiar with, is observational. As many of us like to watch and count migrating birds as they fly by. But here too there are problems, because when watching migration using the naked eye, we can only detect birds up to the limit of our own visual acuity or to the limit of our binoculars. But as we now know, most bird migration occurs at greater height, beyond our visual range. Most migration also occurs at night when we couldn't see it anyway. And we know this partly because of the use of radar. Next, please, ma'am. Next slide, please. Radar use since the 1950s. And this brings me to probably the most famous of all British ornithologists, David Lack, who during the last war was a radar technician. This was his job. And he volunteered to go to Orkney. Nobody else wanted to go there, but he, being a bird watcher, was very keen on that idea. And he saw there these tiny dots on the radar screen that were familiar to all the radar workers and the watchers and so on. They didn't know what they were. They knew they weren't aeroplanes, but they just used to call them angels. And David Lack is the person accredited with recognizing that these angels were in fact migrating birds. But he also, more importantly, realized the possibilities of studying bird migration using radar. And he was one of the first people to work in this field. Now, radar has a fantastic advantage compared to just people watching birds, because you can compare the volume of migration on different nights. You can relate it to the weather. You can assess the altitude that the birds are flying, the directions they're moving. That's completely independent of visual observations. You can use it in all weathers, at any altitude. It has none of the constraints of ground observers operating only with binoculars. The one drawback, of course, is that you can't tell the species. You can tell slow flying small birds from faster flying birds like ducks and waders, but not much more than that. Well, I've got a few slides now, next please, Barry, that give you some idea of what you see. And my opportunities to watch bird migration on radar were on this machine here. This is an ancient Russian radar that became available on the black market and was bought by some Israeli friends working on bird migration. They realized the potential, and it's actually based in it's a mobile radar that's based in a caravan-like structure that you can tow around the country and examine migration in different areas. Now, next slide, please. I want to explain to you now what you can see. And this is just a photograph of that radar screen. Now, you imagine yourselves sitting in the middle of the screen at the place in the middle of the circles labeled Latra. That's where you as an observer are sitting, and all those circles represent different distances out from the radar. And you'll see on the left of the screen a blue line down the screen, and that's the coast. So to the left of that is the Mediterranean, and to the right is the land of Israel. And all that red stuff that you can see, that's all migrating birds. Now, this particular photograph was taken on the 1st of April in 2009 at 9:05 in the evening, so it's pitch black outside. Now, the great thing about this particular radar is that you can lock on to any echo, onto any bird, and follow it for the radar will stay with it for a set period of time. You can choose your time, let's say 10 minutes, so that each migrating bird, each echo, appears not as a dot, but as a line. If you look at it carefully, you'll see the lines on the map. Now, those lines are important because they show us the direction in which the bird is moving, And also the length of the line. By measuring that, you can get an idea of the speed of the bird, because that line is the flight over a 10-minute period. So there's an enormous amount of information you can get from this, and the radar itself will calculate all this on its computer. And if you look at the diagrams on the right-hand side of the screen, the one at the top with a lot of red dots on it, that simply shows the altitude that these birds are flying. The altitude is given on the vertical scale, and you'll see that most of those birds are flying at less than a kilometre or kilometre and a half above the ground. That's 1,500 metres. But there are a few birds flying above 2 kilometres above the ground. The lower graph, just below that one, shows the same data, it just plots it differently. And along the bottom of the graph, you'll see the diagrams there. There's a compass, which shows you the average direction that all those thousands of birds are flying. And the other one shows the distribution of their speed. Unfortunately, the bottom of the screen is cut up, so you can't read the values. But the important thing is that that shows you the kinds of information you can get from radar. But remember that this picture is changing minute by minute by minute right throughout the night. So if you're a poor biologist studying the migration in this way, you very quickly get utterly swamped with data. Next, please. This shows another picture of the same screen. The background color is different, but that doesn't matter because you can set it to whatever color you want. But this is a daytime picture, and this is in the autumn. It's the date's on the top. It's the 8th of October 2002, and it's about midday. And that blue line down the left side of the screen, in the left half of the screen, that's the coastline of the Mediterranean again, with the sea to the left, the land to the right. And now if you look at the blue patterning on the screen, you'll notice that there's a thick stream of migrants, that is. And that's actually all birds of prey that are soaring and migrating and gliding down the Rift Valley. And we know on that particular day that most of those birds were lesser spotted eagles, and the numbers were counted at 36,000, which is nearly the entire known global population of that species that passed south through Israel in that single day. And that line of migrants may have gone back as far as Turkey and down as far as Suez, where they crossed into Africa. And we know about the numbers because the Israelis on this day had a line of observers lying on their backs with their binoculars pointing skywards across that migration line, counting the birds as they went by. And eagles are big, and their maximum flying height under thermals is about 1.5 kilometers, so they could be readily seen and counted. Well, over the years then, radar has increasingly confirmed for us. It's taught us a lot about birds, but it's also confirmed what we thought by observation, that birds prefer to migrate under clear skies with a following wind. The clear skies enable them to see the sun or the stars by which to navigate, and the following wind, of course, helps push them along the route, helps them on their way. Next slide, please. Now, following winds are of obvious importance to a bird. If you can imagine a bird like these grey-lag here, flying at 40 miles an hour, if those birds flew in a wind that was also blowing at 40 miles an hour, they could, in theory, travel at 80 miles an hour because they're traveling in a moving stream of air. Travel at 80 miles an hour with respect to the ground, that is. So that would enable the bird to halve its travel time or double the distance it can fly within an hour. And we know from observations at bird observatories that birds do take off preferentially in following winds. If the wind is opposed, they just tend to stay put and wait for conditions to improve, or alternatively, some species simply fly up high and sample the wind conditions at different altitudes, because the wind directions, as well as the strength, varies with altitude. And if they find the right conditions, then they go. Otherwise, they'll return back to the ground and wait. Well, next slide, please. Regarding altitude, these are summaries from 3 studies from different parts of the world, showing the numbers of birds that are detected by radar at different altitudes on one particular night. And the altitude on this is shown on the left-hand scale, and the percentage of the echoes is shown on the bottom scale. And if you look at the left-hand diagram first, you'll see that this was from the Central European lowlands. Most of the birds there are flying less than 2 kilometers above the ground, but some are as high as 3 kilometers. The middle diagram is from South Sweden, and this is in spring, and the birds are coming in over the Baltic Sea. And there you can see that the average height is much higher, it's probably around 2 kilometers, and there are some birds there that are flying well over 3.5 kilometers above the ground, above the sea. And the last one on the right, that's migration over the Caribbean as measured from a radar on the deck of a ship. And that shows birds that are migrating over the Atlantic from North to South America. And some of those birds, as you can see, are incredibly high, up to 6 kilometers, that's 6,000 meters above sea level. But they're not the highest birds recorded. Birds at about 9 kilometers over sea level have been recorded over the ocean occasionally, or over the Himalayas. So why then do birds travel at such varying and sometimes at such high altitudes? Next, please. Well, these are some data from the Gulf Coast of North America. This is the Gulf of Mexico, and a radar station situated on the Louisiana coastline that is recording birds coming in over the sea from Mexico. And what this slide shows on the vertical scale is the altitude of the densest bird migration on particular nights in relation to the altitude with the most favorable wind on that night. And you'll see that there's a clear-cut relation in that birds are choosing to fly at whatever altitude the bird was most favorable to them. That's the most energy efficient altitude, with a strong wind blowing in the direction in which they want to travel. So these are mostly small songbirds, but it's clear that they do take enormous attention to the wind to get the maximum benefit from them that they possibly can. But of course, next please, Barry, there are also constraints in traveling at higher altitude. Sorry, that was the right slide, the geese again. Okay, yeah. Because as a bird climbs in the air becomes thinner, as you all know, so there's less oxygen and the temperature falls. For every kilometer above ground level that a bird flies, the temperature becomes 7 degrees colder. Now, a typical temperature in autumn in Hampshire, let's say, might be 5 degrees centigrade. So that if a bird leaves Hampshire and flies up and ascends to just 1 kilometer above Hampshire, it's now in temperatures of -2. And if it goes up to 3 kilometers, it's -16. And if it goes up to 5 kilometers, as it might, it's down to -30. Now, the heat loss to birds is obviously great under those circumstances. It might be compensated to some extent by the heat that the bird's body generates as it exercises in flying, but that amount of heat is limited. And at the high altitudes at which some birds fly, they must burn energy, not only to fuel the flight, but also to keep warm. So although winds may be favorable at higher altitudes, there are clearly constraints in flying at those altitudes and costs involved. In fact, the bird faces trade-offs. It has to balance the energy gained for flight in favorable wind against the cost of heat production and reduced oxygen availability. And most of the high altitude flights that are recorded from birds have in fact been in warmer parts of the world at lower altitudes, where heat loss would be less. Now, for many years, the only information we had on bird movements was from either observations, as I mentioned, or ringing. Now, each recovered bird gives us only two pieces of geographical information. We know where the bird was ringed and we know where it was recovered, but we've no idea where it was in the interim. But in recent decades, as you know, next slide please, other breakthroughs have occurred, enabling us to follow individual birds on their journeys wherever on Earth they travel. It doesn't matter if they go to a politically inappropriate area, we still get the records. And the first method that I want to talk about now is the satellite tracking. This is a golden eagle that's just been tagged. The hood is on its head just to keep it quiet while this operation is taking place. The satellite tag is just tied onto the bird in a comfortable way. The radio is giving bleeps all the time, and the messages are received by satellites circling the Earth. The messages are beamed back to Earth, telling us where the bird is. Now, this method is relatively expensive, but it's relatively accurate, but it's very expensive. At the time I was involved with this sort of work, which is now more than 20 years ago, it cost about £3,000 for a single tag. At that time, most of the tags were battery operated, and that of course limits the life of the tag and also adds weight. So initially that very much limited the size of bird that would carry this, and most of the early work was done on either big birds of prey or geese and swans. Next please. Nowadays most of the tags are solar powered. This is you can see the solar panels on the back of this. This is a red-footed falcon. And that bird was tracked on migration from Hungary, where we are now, down to Madagascar and back. But nowadays, most of the tags are solar powered, and they also use the GPS system to give accurate locations. And because of that reduction in weight, because of the lack of a battery, they can be used on much smaller birds. And they've given some remarkable results. Can I have the next slide, please? This was an early example. I think this was the first bird ever tracked on its entire migration. And this was by Bernd Mayberg in Germany. And the bird was a short-toed eagle, which he caught at the nest and tagged in France, and then followed it on migration all the way to Niger, its main wintering area. Now, you can immediately see how better this is than ringing, because you know the position of the bird every date, and those dots mark the roost sites of the bird on successive nights through the migration. So we have its position on every date, we have information on the route, we know all its stopping places, and we can calculate the time taken over the journey, the altitude of the flight, and whether the bird's been affected by weather in any significant way. And not only that, you can take any one of those dots, any one of the locations, and you can look on your PC, you can look at Google Earth and find the type of habitat in which that bird is likely to have spent the night. Well, that's an enormous advance over a single ring recovery. Next, please. Now, that method has also told us the main hazards that birds face. And in the osprey, for example, and this is based on Roy Dennis's work in tagging birds in Scotland, he's shown that most of the mortality on Scottish birds on migration occurred. I expected they'd be shocked, but this turned out not to be the case. Most of the mortality occurs at sea as birds are blown over the Atlantic by easterly winds, or it occurs in the Sahara Desert for obvious reasons. And this work has also shown us that juveniles on their first migration suffer much heavier mortality than do the experienced adults, more or less as you'd expect. Next slide, please. And the same is true for honey buzzards. But in other species, it's also told us of previously unknown wintering areas, so it's extended the known geographic range in Africa in winter. Next, please. I want to move on now to bar-tailed godwits. These are not those godwits that occur in Britain, but others of the same species that breed in Alaska and winter in New Zealand. Now, more than 30 of these birds have been satellite tracked over the years, and the next slide shows some results. This is for a single individual known affectionately as bird E7. And that bird, like the others, flew non-stop from the top of the globe there, from Alaska, over the Pacific to New Zealand. That was a journey of 11,700 kilometers, which took it 9.5 days and nights. That's 228 hours of continuous pumping flight with no rest, no food, and no drink. Now, that particular bird, it was a female, averaged 58 kilometers per hour, all the time traveling at least 3 to 4 kilometers above the surface of the Earth. Now, after wintering in New Zealand, that bird took a different route back to suit the wind conditions at that time of year. And that flew another 10,300 kilometers non-stop from New Zealand across to China on the left-hand side, to the Yellow Sea on the China-Korean border. She took 7 days on that, but her average speed was slower at 38 kilometers an hour because of adverse winds. But after refueling and resting in the Yellow Sea area for about 6 weeks, she then flew another 6,500 kilometers back to Alaska. Now, that's the longest flight ever recorded in a land bird, but up to 70,000 godwits make that journey every year. Not all make it, of course. Next, please. Well, apart from the obvious question of how the birds navigate on a journey like that, there are two other questions that arise. First is, how do they carry enough fuel for a journey of that type? And secondly, how do they manage without sleep? Well, at takeoff, it turns out that these godwits more than double their normal weight. Some 55% of the total body weight at takeoff time from Alaska is fat. But in order to carry so much fat just before takeoff, these birds also shrink all those body tissues that are not concerned with flight, including the gut, for example, converting these other tissues into flight muscle and fat. Now, the fat tissue of the bird, the flight muscles, the heart and the lung expand, while all other body organs shrink, reducing unnecessary weight gain to a minimum. So this, of course, no change occurs in the brain. But this immediately tells us that birds are not like aeroplanes. They don't simply, at least birds of this type, they don't simply land, refuel and take off again. Fattening in a bird like this involves a lot of internal reconstruction to give us the maximum fuel with a minimum of other tissue. Now, regarding sleep, we've learned since this work was done that birds may not totally do without sleep, because birds apparently have the ability to rest one side of the brain at a time. And the assumption is that a migrating bird might rest one half of its brain and then the other, and this way get some sleep, as it were, for during migration. So for most of the migration, they may be in effect operating on half a brain, but maybe not for takeoff and landing. But anyway, this is a field that's advancing rapidly, and I'm sure we'll know a lot more about this in the years to come. But all this was discovered by satellite tracking. Next slide, please. I just want to touch now on the second method of recording migrating birds in detail, and this is the use of geolocators. This is the cheapest method available. When I was involved, it cost about 50 quid a unit, but this is effectively a data logger, which is, in the case of shearwaters, is attached to the leg like a large ring on the bird. But the problem with the method is that to get the data from the data logger, you have to recatch the bird and download it to a computer. Now, seabirds are absolutely ideal for this work, or at least most species are, because they return to the same nest sites year after year. So you can catch it and tag it in 1 year and catch it in the same nest burrow or whatever the following year and recover the information. But what the geolocator does primarily is to measure day lengths. It records the time of dawn, and dusk every night and every day that the tag is on the bird. Now, in knowing that, in knowing the day length in relation to the time on breeding areas, you can work out retrospectively where in the world the bird was on particular dates. You know the longitude from the time shift, and you know the latitude from the day length. But these estimates you get in this way are only rough. The main problem is that latitude is difficult to judge at the equinoxes, because their day length is the same, 12 hours worldwide. So there's a period around the equinox when you don't get reliable readings. But nonetheless, it's a very useful method, particularly on birds that are undertaking long migrations. Next, please. And these are some data collected in the early work by Chris Perrins and colleagues who are working on manx shearwaters on Skomer Island. And each of these dots marks a location recorded by Geolocator. I think there's about a dozen different shearwaters studied in this. Now, you can see the birds, they're all tagged on Skomer Island. They migrate down the west coast of Africa and right across to Brazil, where they spend the winter. Now, we knew that from ringing, but what we didn't know is that on return migration, they don't simply retrace their autumn track, but turn northwards up the west side of the Atlantic and cross the Atlantic in the northern hemisphere, taking advantage of winds. I don't need to remind you perhaps that the winds move circularly, clockwise in the northern hemisphere and anti-clockwise in the southern hemisphere. So through on this entire migration, the birds are making maximum use of the winds available at the time. Now, you'll notice that there are quite a lot of spots on this map that are over land, over Europe and over South America. And the assumption is not that shearwaters are flying over land or over Europe or South America, but these are simply due to errors in the location estimate. Because if this gadget is recording day length, you've only got to imagine that on a dark morning, cloudy morning, it's going to record day length as starting, or daytime as starting later than on a bright sunny day. And that leads you to misestimate the position of the bird. But on this scale, it's not important. It still is almost irrelevant on the length of migration that these birds are making. But the advantage of the method is its cheapness. And these geolocators are developing all the time, and they're now so light in weight that they can be used even on songbirds. The latest ones weigh only 1/3 of a gram. That's small enough to fit on a bird like a robin, let's say, or a blackcap. Well, I think I've probably overshot my allotted time already, so I'll end at this point. If I can just make a few concluding comments. But the main points I've tried to make, which you realize already, that birds are quite really remarkable creatures. They perform feats on migration that are almost unimaginable to us. Unimaginable in terms of the distances they fly, the non-stop distances, the altitudes they fly, the way they store and use energy. All these fields, we've had huge advances in recent years, and technology has continually provided us with new tools and pushing forward our understanding of what birds are capable of. So we live in exciting times for migration research. Okay, thank you very much.
Ian, that's fantastic. Thank you so much for that. Really appreciated. We do have a little time. A number of members posted a few questions before in advance of the talk. I probably haven't got time to go through all of them, but I will just try and pick out one or two, Ian, if that's all right. I think I know you've covered, try and track as you've gone through your presentation. I can see you've covered one or two. So I'm going to cherry pick. So apologies for anyone that did post a question that I'm not going to pick out. I'm just trying to pick out ones which may be of broad interest. So here's one about, do birds set off individually or in associated flocks? I'm sure it may be species specific, but is there a general response to
it is a species, yeah, it is species specific. It really depends very much on whether the bird is a flocking species or a solitary species. Cuckoos, for example, set off on their own, but waders like, I don't know, knot or dunlin, they set off in flocks and remain in flocks throughout the migration. Geese also. So it does vary with species. But there are some birds like raptors, soaring raptors like, I don't know, honey buzzards, that would set off individually from their territories, but would soon club together as they all converge on the same migration route down through Africa. But generally, it's variable.
Thanks, Ian. Kind of connected, but although the question is specific to osprey juveniles, but again may be relevant to other species as well. Cases where juveniles are left behind, how is it that juveniles know which direction to go if they're not actually following parents?
Same as any young bird of most species knows, it's inherent. The direction, we know this. A lot of work being done on the inheritance of bird migration patterns, and individual birds inherit both the direction and the distance from their parents. So juvenile birds that are left completely alone, like young ospreys and young cuckoos is the obvious example as well. Young cuckoos leave Britain about a month later than the adults, so they're totally on their own. They find their to a suitable wintering, they get to a suitable wintering area entirely because the route and other things are inherited in the bird.
This one's got a broad brush in, so maybe an unfair question to ask, but I'll try. You made a specific, the specific example was the black-tailed godwits in terms of numbers of days taken to complete its migration. I'm sure the numbers of days varies again across species. Are there some other examples that could, based on data?
Yes, yeah. Well, obviously, as you're implying, Barry, it depends very much on the length of the journey.
Yeah.
The longer the journey, in general, the longer they take. But the journeys take a lot longer than you would think. I mean, short journeys are okay. If a bird's just migrating within Britain, it can do that in 1 or 2 days. It may do it in a single non-stop flight. But if it's going to the south of Africa, it's a very different matter, because for one thing, it's got to stop and refuel several times on that journey. And some bird migrations take up to 3 months or even longer, simply because birds are stopping for long periods to refuel. It's been calculated that birds, well, it's calculated and tested and proved that birds about the size of a chaffinch, for example, if they're going to migrate for 7 hours, they've got to feed for an extra, if it's going to migrate for 1 hour, it's got to feed for 7 hours to get enough fuel to cover 1 hour's flight. So the ratio of flight to stopover in a bird of that size is in the region of 1 to 7. For a larger bird, like a swan or a goose, that has to feed for relatively much more of the migration period in order to accumulate the fuel necessary for it to fly. So as the bird size increases, the ratio of flight to stopover is changing all the time.
That's great. Thanks, Ian. I think we've got time for probably a couple more. One I'm going to pick out here is on species where there's partial migrants. So some members of a species may migrate, others stay put. In those cases, does such a bird always adopt the same strategy, or do they switch year on year? What is there any?
Some partial migrants switch year on year. Very often it's the young birds that go and the older birds that don't. But in many species, you can have adults that go in 1 year and don't in another. It's dependent on conditions at the time. And if it looks like, or if it's a winter with very little food supply, birds are very likely to go that would have stayed had it been a better year. So individuals vary in that behavior. But the situation is actually more complicated than that. What I've described as a situation in which we call situation in facultative migrants. These are birds that migrate if they have to, but don't otherwise. But there are also obligate migrants that have to behave as they're genetically programmed to behave. And there are some species in which part of the population is genetically programmed to migrate whatever, and another part of the population is genetically programmed to stay put whatever. So you can get partial migration. because some are programmed to migrate and others not, or you can get partial migration because everybody's a facultative migrant and some decide to go in certain years and not others. I hope I'm not confused the situation even further.
It's complex.
It's complex, yes. Yeah.
I'm going to ask, before I just finish on one final one, Ian, just before seeking to wrap up. And that's, I mean, you've covered a huge amount in the course of the last hour. There's been lots of exciting developments, and you've made reference to a number of those during the course of the last hour. But as you reflect, what perhaps has been one of the most exciting insights that's been gleaned in more recent years? Anything particular stand out that we didn't know, but only recently we discovered through the various research that's taking place?
Well, if I'm allowed to say two things here.
Of course you are.
This is obviously a personal answer. One of them is the realization and proof that birds can detect and use the Earth's magnetic field to orientate by. That is, to me, a staggering thing, because we have no magnetic sense of this sort ourselves. To realize that there are other animals that can use it in a very precise way is a staggering discovery. And part of that amazement is that they actually do this through their eyes. This is the organ that senses the Earth's magnetic field. And that to me is one of the really staggering developments in recent years. The other staggering development for me is just simply in terms of amount of information, and that concerns the migrations of seabirds, because we had very little information, reliable information on seabird migrations before we were able to track them on migration using satellites. Because you relied on ring recoveries, and you found a dead bird on the beach with a ring on it, but you'd no idea where that bird had died. It may have drifted in the water for several hundred miles or something. So the data was not necessarily that reliable. But putting satellite tags and geolocators on pelagic birds like shearwaters has revealed some absolutely amazing results. Where they go, the time they spend at sea, and the amount of time they spend on the wing. It's just totally staggering. And it's also shown there are areas in the sea that we didn't know about that are extremely rich in food and feed not only birds, but mammals as well. These are stopover sites for migrant seabirds. So anyway, they're the two things that come to mind immediately.
Well, no, that's a fantastic, thank you, Ian. That's a fantastic way to finish. Now, without doubt, I know we could go on for another hour, and we've not opened the floor up for questions tonight, just purely because the amount of information you've been so good to share tonight. As Keith said at the head of tonight, thank you so much, Ian. We've been really privileged to have you with us tonight. I'm sure, I know I talk on behalf of everyone that's joined us tonight, a real big thank you for giving your time and sharing your knowledge, which is obviously drawn from all those great years of research that you've shared with us tonight. So Ian, thank you once again for tonight, and a good evening to you and to everyone else. Just as FYI, as always, tonight's has been recorded and will be posted to the HOS website. So if you struggle to remember everything, and this is one which is this huge amount of information to remember, it'll be there to listen to subsequently. Probably posted by sometime tomorrow. So Ian, a final thank you so much tonight, Ian. Thank you very much. A warm evening to everybody, and we'll see you all again soon. Ian, thanks again.
Thank you very much.
Very much.
It's been a pleasure. Thank you.